So we're going to have a bit of a look at how it might sound when they are performing.
DJ Orbit on the left, and DJ Odelin on the right.
So obviously these sounds that they are scratching on, they come from the computer. They recorded them themselves because they are mentioning their own names, and probably they don't have their names on real vinyl. So.
Beats and rhymes. I'm feeling trapped. Can't stop the bro. It's impossible. Can't stop.
And you see, what he did here was that he pressed this panel, and that changed the sound. So it controls the computer to change the actual sample that is replayed. So you can switch in between different songs directly by pressing these pads or different sounds. And you can make music. And there you also saw that he was re-triggering the same sample position several times to have it taking this saxophone tune and making essentially new music from old music. So that is what DJing is about, and these guys, they are really, really skilled. It takes years and years of training to get to the point where they are, that they can actually not only scratch, but make it sound good. At least to me, it sounds great. So how does this work? What is the technology behind this magic that you can get the computer to act as a vinyl player? So I'm going to take you through that, and that is a Rust journey, and it starts with MATLAB or Octave in my case. So I was trying to model the control signals and see how we can recreate the position, because the important thing here for the computer to know is where on the record are you at the moment. And it will use this information to replay or resynthesize the sound output. And now I'm a bit handicapped because I have just one hand. The other is holding the microphone. So how does this work? Let's see if we have a network here. Not so much. Yeah, but it's connecting to Tune, and I think it should work. But in the meantime, maybe we can see this. This is the repository that is under Per Lindgren, Face Track, and it's open, so you can go to here and have a look at it. And yeah, I think now it has a README, but it's not shown here because we don't have the latest version. Right, so we can stop there and maybe take a look here. So finding out position is a common problem. I mean, we are doing it now when I'm scrolling here with the scroll wheel. It uses a quadrature detector. So it's actually tracking the position of the scroll wheel by a phased signal. So there are two signals. In this case, they are like square waves with a phase offset. And then there are some either electronics or software that actually unfolds this into a position and direction. So you can both get the direction and the speed, and out of that, you will be able to track the position. And this final record uses a two phase-shifted sinus signals encoded as left and right, because that is what you have on a stereo recording. So it's a stereo waveform with two sinus signals. It has been hugely successful. these DVS systems are widely used by both live DJs and music production. And it's very robust and accurate tracking based on this. And flexibility, as we see, they are scratching and DJing on sounds that they made their own. That's not available on vinyl. So the solution is a well-known tracking problem. So it's not a new thing that I invented or they invented, the ones behind these systems, but it has a well-established theoretical foundation. And I will show that in a bit. So we use Octave, which is a MATLAB-like tool for rapid prototyping and visualization of waveforms. And then later we'll show a one-to-one manual transition or translation of the MATLAB or Octave code into Rust. And here there are some interesting functions that are not part of standard Rust. So we are using libm, which is a great library for mathematics. And we are using the RAND library to get random numbers because we want to test how resilient to noise this tracking is. And then we are using the plotters crate. Anyone has seen that? Maybe you're already using it. It's great. It's not so easy to use, but the results are good. And then for quality and assessment validation, we are using CSV format, so we let Octave output the sort of golden model results, and we read them into Rust, and we are computing the error. And in this case, we are using, I think I can show that, this mean squared error function looking like this. It's also a well-known measure for assessing quality. And we can see that we get an excellent correlation in between the MATLAB code or the Octave code and the Rust implementation. And it might even be that the Rust code is actually more correct to the problem than Octave, because this libm does a lot of smart things when it comes to calculations of small angles. Well, x is near 0. You can read more on the Git if you're interested in more details. So without further ado, we're going to look at this, where we have some Octave code, and we'll start with this phase M. So what we're doing here is that we're actually over a period of 48,000 samples, which is a common sample rate. We are producing a sinus and a cosinus signal. So these are then phase shifted according to each other at the frequency of 2 Hertz. And the sample time is 1 second. And what we are doing here is to compute the arctangents 2 function. The tangents function is the relation in between height and width. So you can use that in trigonometry. And arc of that is just the inverse function. So you can get a phase value out of the 2 left and right signals. Essentially, it says how far in, if you have a sinus signal like this, how far in are you on that? And by having 2 of them, you can discriminate in a much better way. So that's why we have left and right. That also allows us to track the direction, as we'll see later. And then there is a problem here. That is, when we are reaching the end of the first period, a new period starts. But the sample values will be exactly the same for the first and second and third and fourth period. So we have to check when we are entering a new period, and that we're doing here, and we call that the wrap value. So when that happens, that means that we are increasing the wrap value here, and that is used to create an unwrapped signal. And now we can run this. So we can start the terminal, and we can have MATLAB or Octave. So we start Octave like that, and we can CD into octave, and we can source this MATLAB script, which is called phase.m. So what we are seeing here are three graphs. The first graph is the sinus and cosinus, and we can see here that it's two periods. So this is the first period up till here, and then the second period up till here. And then we can see the A tan 2, that is this, the value, we can see that it's increasing up to half of the period. Then we have the next for a full period. It's increasing again for half a period. And then we have the unwrapped values over here. So this one is tracking the total position. So it takes the wrapping into account. So this is it's nothing spectacular with this. This is a well-known technique for finding a position. You can use it inversely for tracking time if you know the frequency here is stable. So then you can also see how long inside a function you are in terms of time. So time and position might be interchanged. Right. So you get the basic idea how this works, that on the vinyl we have these two sinus and cosinus signals. We read them through a sound card. We just sample the signals, and we detect the phase of it with a tan 2 function, and we unwrap into an absolute position. Well, absolute in relation that we know the start position, but in general it will be a relative position. But the idea is the same. Okay, so how does that work if we change the frequency over time? So we have a phase inc here. Let me see. It's awkward with the microphone. Now what is this? Phase. Here we go. Inc.m. And then we see unwrapped signal looking a bit like this. So what's happening here is this is the arctan, and we see that the density of these are increasing because we're increasing the frequency. We can also look at this graph showing that in the beginning we have a low frequency that we start out from, and then in the end it will be chaos of sinus signals here. So the density is increased here by the rate and frequency is increasing. And we can also see that we have a growth here in the position. So that looks good. It's expected, right? This is exactly what we want. So what about direction? Can we say something about that? Well, this one. This one is interesting. We start out with a signal that looks like this. Here we go. So we start by forward, increased sample positions, and here the frequency goes to 0, and here we will have a negative frequency. So we are sort of pushing in relation to the DJ. He would push the record forward and then drag it backwards. And this is the position where it ends or does not move at all, so it's the turning point. So how would the phase angle look like? It will look like this. Here we are going forward, and here we are turning, and here we are going backward. And we can also see that the position is increasing here while it's decreasing over here. Here it's first increasing, then 0, and then starts to decrease. And the unwrapped counterpart looks like this. So this is the actual tracking of the signal after that we have done the unwrapping of it. But it's not so obvious to see directly from this but we can also see here that the red or comes before the blue, and here we have the blue coming before the red. I don't think the colors are really consistent within the graphs. Probably possible to give them some deterministic colors, but I'm no Octave expert, so I just got this to work. Not anything more. Phase noise, so what about that? It's important for any tracking that it's resilient to noise. So let's have a look at this. How does a noisy signal look like? Now, this is really, really noisy. This is really, really noisy. Here we have about 25% noise in comparison to the actual signal. We can still see that since the noise is just overlaid over the sine and cosine, we can still see that they have some form to them, but we have a lot of uncertainty. So how do the tracking deal with this? So we can look at, let's see, maybe, yeah, we can go directly to the solution. Here we see that we can see that the A10-2 has a lot of uncertainty to it, but we can still unfold or unwrap the correct signal. So on the average, if we make a bit of a low-pass filtering here, it would look perfect again. So that means that it's really robust. 25% noise, that would be approximately 2 bits. If you are sampling with 2 bits, then you will get that bad signal to noise ratio. But we can push it. This is the phase noise. So let's have a look at this, how it looks like. So here is just to offset, the rand function gives random values in between 0 and 1. So we want to have it centered around 0. And here is the weight. So the signal would go from -1 to 1. That's why 0.5 means that it's 1/4. But let's double the noise. Oops, not there. Let's double the noise to 1 and see how that performs. And now we are really, really noisy, as we will see. So let's go back to here. Maybe it did not work. Let's see. If I do it like this, I don't see the end of my, because this one has, I want to close this. And I want to close that one. And I want to close that one as well. I don't know why it behaves like this. We can take this down. And there are still some, yeah, now we have the right one. Here we see the one that has a lot more noise. So let's see how the phase unwrap. No, this is the wrong one. And let's see here, this is also the wrong one. So let's rerun this again and hope for the best. Phase noise. Yeah, so now we see that we have a lot more noise here, but we are still tracking perfectly the transitions. The unwrapping is working. So let's go really, really mad and put 1.5 here. That means that we have 75% noise in the signal. And we can see that the noise here increased by that, but the unwrapping succeeds. And here we have the actual signals, and they look like shit. Obviously, it's very, very noisy. So what we can conclude from this is that the tracking here is very, very stable, even under extreme noisy conditions. And think about the DJ, he's pushing the platter, the vinyl, back and forth at a very high rate. And you have this mechanical device that you just hope to work. So it's this cartridge or pickup. It might bounce around a bit. So it's really good that you have a stable tracking algorithm. So we can push it a bit more, and then you will see how it breaks down. If we put exactly the value 2 here, that will mean that we have the same amplitude in the noise signal that we have in the actual signal. And as we see here, there is no order in anything, it's just random. Well, maybe you can sort of feel that it's an increasing signal, but yeah, well, it might also be dependent on how the rand function works. It's not really random numbers, it's a sequence that a computer computes. So it's deterministic. And well, that might be an artifact of that we are seeing here. But essentially, this will never happen in reality, so we don't need to worry too much about that. So we can put it back into the like more reasonable 0.5 and 0.5 over here. The algorithm here is exactly the same as I showed the first time. The only thing is that we also have to check for the wrapping in an opposite direction if we are going to be able to track the record turning and going backwards. But besides that, all is equal. And here it's just plotting code. So the MATLAB part of it is really, really simple. Any questions so far? This is certainly useful to other things than DJing, but mostly to DJing, I would say. So examples here in Rust. What we have here, let me close that, is a Rust program. And we could put this face.m in parallel just as a comparison. And now I'm not much of an Octave or MATLAB programmer, which means that I write MATLAB code like I would have written Rust code. So we can see here that this is setting up a range. Here we are doing the same thing with a range in Rust. We are computing the sine and cosine into a vector directly in this case. Here we are doing it for each element, element-wise. But besides that, we can see that the code here, we are checking the tan2, blah, blah, blah. Everything is essentially the same. So we can see that this for loop is exactly the same as this for loop. And the plot here corresponds to the plot here. And then we also do a quality assessment. So we can try running this. If I now, not sure why, it says that it's terminate task, okay. Well, it did terminate in the end. So what happened here is that it computes the accumulated error for these 48,000 samples, and it's really small, and this is the MSE, so it is the mean square error. And it's even smaller because each error is so small. I don't know if these are the right measures for this purpose, but at least it's some measure, meaning that we see that these correspond really well. And it's the unwrapped signal that we are comparing. So I put some code in a library here, which does some like file loading to read a CSV file. Here, what we're doing here is the quality assessment, and it's just iterating over these two arrays and accumulate the errors and the accumulated error and the mean square error. So it's very simple Rust code in order to compare these two, and then it just prints accumulated error. The rest of this library is horrible. It is the plotting code for the Rust part. I don't know exactly what happened here, but we can have a look. We have SVG files generated. and we can preview the SVG file, and it looks like this. We can relate that to one of these, the initial one that I showed from MATLAB. The wrapped signal we can look at as well. That does not work anymore. Sorry, let's see again. So we have the wrapped signal. Preview that. Why is it? Yeah, it is working. So this is the wrapped signal, and the unwrapped signal. Preview of that looks like this. So obviously they look very similar to the graph that we saw plotted by Octave earlier. And also the error assessment that we did showed that these were the same. We can do exactly the same for the phase decrease and the noise part. Maybe the noise part is the more fun thing to look at. So we can run that and press run here. Okay, it's already done, I guess. So it's really fast since we are just processing 48,000 samples. And now we have SVG files for this. So this is the noisy signal. What we have more is the wrapped signal over here. No, we don't want to look at the SVG file, but we want to print it. So this is the that part, and the unwrapped is this. So we can see that also for the noisy part, it worked out. It's harder to do error estimation if we have noise involved, because the noise will probably look different from MATLAB and from Rust. What one can do is to generate a file with the noise, so we have a replicable noise, and then it would have been possible to compare. I didn't do that because I think this is simple enough to trust that the measurements that we did earlier on also hold in the case of the noise. So now we know how, or at least have a good idea, how we should be able to replicate or at least track the control signal. So what can we do with that? Well, we can do what they used to do. I mean, have the computer just replaying a sound according to the positions that DJ gives through the vinyl. But we can do more. And this is, to my knowledge, no one has yet done. And that is an editor. So this is Cut Creator. I think it's the first editor for DJ scratches. So what we can do with this, it's written in eGUI, is to open it up like this. And here we have a plot of the record position. Maybe, can we get this to work somehow? Well, nothing works. This is...
Well, it worked half an hour ago.
Yeah, but obviously it does not work now.
Yeah, sounds like it could be better.
Or just, we try to...
Yeah,
Yeah, that was the only thing needed. Okay. So what do we have here? Well, we have the sample to the right. We can enlarge that if we want. So this is just a sample. It sounds like something like that. And here we have the scratch positions. So that would correspond to this unwrapped signal. And here I'm using splines interpolation in order to be able to edit the positions. So here that would mean that the sound will go forward, backwards, forward, backwards, and then finally forward. So we can press this sample button, and then with a bit of luck we can find it, and we can read. So we had a wee, wah, wow. And I started this without any knowledge of eGUI. Actually, I think it was one of you guys that showed his iPhone that he was running eGUI on it, and he had a snake game running or something like that. Yes. It was maybe not a game, but at least it showed that it was possible. So I mean, it is possible. And eGUI is quite nice, and a direct mode renderer for GUI applications. So what you write in your code is going to be displayed as is. So it's nothing. You don't set up a complex data structure in order to capture the layout, what you want. But it's very, very direct, and it's easy to do things like this. So we can actually have it working. If I know how my GUI works, Control O for oh, okay. The thing is that it opened this here. So we can have another one here, no, like that. So we can edit multiple scratches at the same time, and we can, these we can shift click and like this, and we can remove, or we can also undo with a bit of luck. Maybe that does not work. Well, maybe it does not work with two open windows. This would, in the future, represent the fader position. I did not yet implement that. But there is a lot more that can be done. We can load different types of samples here. These samples can be edited with a bit of luck. Yeah, so we can, now this does not completely work. Yeah, in any case, you should be able to scroll. Yeah, you can grab and offset the position, and you can zoom in and zoom out, which affects where these cuts are sort of related to the actual audio sample. So it gives you a lot of flexibility when it comes to the reproduced sound. And the idea is that it should be really, really fast for a DJ to use, so everything is shortcutted, so you can enable and disable different tracks just by a direct selection, a bit like what they were doing when they pushed these buttons. So the idea is that it should be a really tactile tool for working with scratches like this. And then, well, I don't know if there is so much more to see. We can take and grab, and we can also push around samples. You can see that these knots here cannot go over the edge. Instead, you would be able to do something like, I'm not sure if this works, but yeah, you can grab many of these and offset them in time. And these time slots here would be a representative of the beats in the music, so you can align them to certain beats or positions in the song where you want to sort of have this sound overlaid. Any questions? This is completely open source, and anyone can contribute to the world of DJ scratches. Yes?
Hey, quick note about the question policy. We have a microphone here, so I'll bring it over to whoever tried to get my attention, so I bring the microphone over.
Yeah, thank you. Amazing presentation. I just want to ask about the basics from the beginning. So did I understand you had a picture where you had these two sine waves with a phase difference, and the frequency was increasing to the right?
Yes.
And is that what you put on the vinyl? So you have a vinyl with left and right channels?
On the vinyl, you have just a fixed frequency. So like 1 kilohertz is good, because then it allows you to push the record 10 times faster than nominal speed and still be within the limits of what a magnetic cartridge can pick up. So
all right.
So what this the graph that looked like that maybe that would symbolize that you're actually increasing the speed of the record. So it starts from very low speed and then you're pushing the record very fast forward.
Yeah, that makes sense. I was thinking about if you lay the needle down somewhere on the vinyl, then it doesn't know the position at all.
Position. It does not have any information on where it is initially. That's why they have these buttons to start a sample. So they use this to trigger a specific starting point. But there are also more advanced ways of doing that where you overlay a positioning signal. And that is also a possibility to do. And then the decoding of that would be a bit more complex than this.
Cool. Very, very interesting and informative.
So records are not linear in the sense that the frequency is not represented linear. There's some curve to, because otherwise a very low frequency would be too long. So there's some sort of curve they apply to the signal before when it's recorded, and then there's the inverse curve done when the signal is played back normally.
Exactly.
So are you actually capturing the raw signal, or are you running it through this correction curve?
What you're talking about is this RIIA.
Yes, I didn't want to say that because no one knows that, but that's what it's called, yes. I wanted to say what it does.
Yeah, well, since we are just concerned with the phase angle, the amplitude of the signal, we don't need it.
Right, so you don't, because
we don't need it for tracking, which means that, it's actually a good thing that this curve exists, because it plays in our hands actually regarding the robustness of this. But we can take that offline and I will discuss why it's like that. Okay. But it's a good thing that we have this compensation or sort of filtering of the signal.
Yeah, that is like a...
Thanks. How big is the impact of using the libm library for the 8 and 2 function?
The implementation?
I mean...
or do you mean the execution time for it?
No, I mean mostly the error. Like you're now using the libm functions 8 and 2 instead of just using the standard libraries 8 and 2 functions. Is the 8 and 2 function from the libm function much more accurate, or...?
From my understanding, it tracks the problem when you have, it says already here, maybe it was somewhere here, 8.10.2, this is from there, this is taken from their website. And it says it produces the correct results even for angles near pi divided by 2 or minus pi divided by 2. So my understanding of this is that the A tan 2 is problematic because you run into rounding errors, and actually what it's called is underflows. And if you don't handle these underflows, or if you handle them incorrectly, you might be way off. And their implementation, to my understanding, is never way off. So it takes this sort of underflow conditions into account when producing the result.
Did you first try it with the standard libraries?
No,
8 and 2?
I'm not even sure that this function exists in the standard library.
Oh, I think it does, but I might be wrong too.
It might. But I found this with the first Google search, so
yeah, thanks.
that's the plain reason why I used it. Yes.
Yeah, so I noticed you use a lot of 64-bit floats for this, and I guess it doesn't matter on a fast computer like a laptop, but if this was implemented on like a microcontroller in like hardware, have you tried using like smaller data types with less precision?
No, I haven't for this experiment. I haven't tried it.
Okay.
Actually, the playback that I showed, that used just 32-bit floats.
Okay.
So for the actual implementation, I will probably settle for 32-bit. if it seems that we can get sufficiently good tracking because it's more computationally effective.
Yeah. A lot of microcontrollers don't have floating point units, so they use fixed point math.
Yeah,
usually
that's
16
also
bits.
possible. And I haven't looked at the implementation details that closely yet.
Okay.
And the idea is to this code will in any case probably run on a laptop or similar. So it's not an embedded for now at least.
Okay.
So what is the takeaway here? Well, we can make a lot of funny noises with the help of a computer, a turntable, and a cartridge picking up this control signal. And I can show you this. No, I could not because I closed it. But these records that have this time code on it, they are quite widely available, and they cost like I would say €15 or something. So it's not a super expensive thing to get going with. And you can just use your normal audio interface on the computer if you're satisfied with just one turntable or a usual sound card with multiple inputs. There is nothing. You can actually connect to that directly if you want. If you have a converter for the vinyl, you need to have a preamp for your vinyl player. This is not the only way to do it. There is also a wireless solution that is called Phase for some reason, a French company that developed this, and it uses an accelerometer instead of the control vinyl. So you put an accelerometer on the platter to track its position. But essentially what it does is to replicate these sinus and cosinus signals out of it, so it acts as a turntable in the end. So they made just the sensor part a bit different, but the actual tracking is done in a similar way on the computer. Yes, you have one more? They all also do that, but their protocol is not open. Yeah, if you want to have a go at it, please. Yeah, I have. Yeah. Yeah.
It's on.
So you had the interesting noise analysis at the beginning. I had another concern that one of the most scary bit about signal processing to me is the concept of aliasing. So what if you spin the record too fast, and then you basically see those signal transitions all the time? Now, can you spin it like exactly the speed where you would think that where the software would think that it's spinning the other direction or something like that? Or
I don't think
maybe it's not a problem if you're spinning it so fast it becomes.
Yeah, I think
too bad anyway.
As I said, the problem with having it stored on vinyl, originally the sort of carrier wave here, is that when we speed up the record up to 10 times, then we have a 10 kilohertz, not a 1 kilohertz signal. If we do it 20 times, then it's questionable whether the pickup, the actual cartridge, will be able to reproduce this as a sine wave. And also the sound card is so limited. In this case, it was 48 kilohertz as a sample rate. You can go up to 96 or something. But I think the physical limitations of the vinyl would hit us before the sound card or the sample rate is a problem here.
Makes sense. Thanks.
Yeah. So that's the idea, at least. And in practice, this is very much used, and it is replacing vinyl because vinyl is hard to come by. So a lot of DJs are using these systems, both the phase one and the one with control vinyl. So please approach me.
Yeah, there's
One more question.
Yeah.
So you showed the very neat editor where you were able to like simulate these scratches and then reproduce the audio. Have you experimented with doing the reverse? So basically recording the scratching signal that someone is making on a physical vinyl with the signal, and then like recreating those, like constructing those control points in your GUI that you could then edit later and like improve on the scratching performance later on.
Yeah, well, actually, that is exactly the next step. But I want this to work within a DAW, in a digital audio workstation. And there you are presented with sample buffers from the DAW, and you are returning sample buffers. And you can have samples incoming. So this signal that we were picking up from the vinyl record could be presented to the plugin, and the plugin could do the analysis online. And then we can have some sort of I would say splines alignment function that tries to minimize the error of the splinification, so to speak. I haven't done that, but it's certainly on the to-do list. And since it's an open source project, if you find this fun and interesting, please approach me and we can discuss how this could be done. Because I'm no expert at this yet, so.
Amazing, thank you.
Okay, I think we are going to cut off the questions at this point. So the update on the timetable, or not much of an update, but the fact is that the pizza will be arriving in something like 10 minutes. And after that, I think we'll be, so let's have a break until that so we can handle that with minimal hassle. I'm going to need like 2 or 3 volunteers because it's actually quite a logistical issue to get 17 large pizzas upstairs from down there. So I'll be open for applications in several minutes. But other than that, after the break, we will be continuing with the more traditional theme of Tampere, that is embedded systems. So I think we have 2 talks that go closer to that kind of theme. So there's actually quite a large community of embedded Rust going on in Tampere at the moment, which I am very happy about. And I just, somebody came to me during the presentation to say that there's possibly some job openings also that they would like to talk about. So would you like to introduce that now since we have the 10 minutes, or do you want to take it later? Great, excellent.
I can just mention one thing regarding USB. You want to have the position signal sent over USB instead of using these sine and cosine signals, right? That was the idea. Yeah, but the problem is that it's much harder to work with USB in a timely fashion than it's to work with this audio signal, because the way that the audio interface operates is that it has a minimal buffer, and then it just sends that over a USB to the host computer. And the host computer API for handling audio class data has been optimized for performance. So that part, believe it or not, both in Linux and Windows works, which means that you will get presented with extremely low latency. You can have buffers down to 32 samples, which means that you have 1 millisecond approximately of delay.
I guess they use either product.
Yeah, well, I don't know what magic lies behind, but it works. So low latency is perfectly possible using audio class devices. Yes. It's a bit harder to do with to rely on the kernel and drivers and everything to get timely data in other USB formats. So,
I'm thinking the same.
Yeah.
So we continue the discussion later.
Yes. Okay. Thank you very much.
Okay, so I won't take much time, but just wanted to say that if you want to turn Rust into money, then we have an opening for Rust developer in Radiator Software. We are doing network security systems, and we have team of about 10 people here in Tampere and customers around in 160 countries around the world. So network authentication, authorization and accounting and stuff related to that. So about a minute and you can ask me more if interested.
Okay, so I guess it's 5 more minutes or so. Yes. I'll be waiting, checking my phone. You are. Yeah, let's hang out, discuss, whatever.
So, hello, I'm Pavel and I'm a master's student at the Luleå University of Technology over in Sweden. And I'm here to talk about Syncrim, which is this tool that I've been developing as partly my master's thesis and partly a hobby project. So I'll start by covering some of the background, so the tool hopefully makes sense to you. And then I'll tell you a bit about my experience building a simulator like this in Rust, along with some takeaways and hopefully a live demo. And I will wrap up by showing some use cases and tying this whole thing to reality. So Syncrim is a synchronous circuit simulator, but what does that even mean? A synchronous circuit, at least as far as Syncrim goes, is just a collection of components and the connections between their input and output ports. So a component has some inputs and some outputs and maybe a state if it's, for example, something like a memory. And the outputs are just functions of the inputs and the state. So this might not make much sense, so I'll show you a quick example. Here we have a simplified version of a typical program counter circuit. So it's something you might see in an instruction fetch stage of a processor. And the idea here is that we want to increment the instruction address by the width of an instruction on every clock cycle. And in this case, the width is 4. So we have an adder. I don't know if I can maybe point with my pointer. You probably can figure out what the adder is. We have an adder, which is a component that just adds the 2 inputs. A constant 4 on one of the inputs, and the second input is just the output of the circuit. So let's see if we can figure out what the output is, which in this case would be the instruction address that we forward to the instruction memory. So we initialize the bottom input to a 0. The constant gives us a 4. 0 plus 4 is 4, so the output is 4. But if the output is 4, the bottom input becomes a 4 as well, and so the output is 8, and obviously something is wrong here, and this circuit is invalid. An important distinction to make is the difference between combinational and sequential components. You can see the combinational component as always being evaluated, like our adder, while a sequential component is only evaluated when the simulation is stepped, so we prevent these combinational loops. In this case, we can put the sequential register on the bottom input, which just mirrors the input as the output whenever the simulation is stepped. So here the output of the register is our instruction address, and you can sort of see how the circuit works in the bottom pictures. In a more complicated circuit, we can run into some pretty complicated data dependencies. In this simple circuit, the instruction memory uses the instruction address to produce its output, and so the register has to be evaluated beforehand. If we treat the components as nodes and the wires as edges, we can look at the model as a directed graph. And any topological ordering of this graph will give us a valid evaluation order. And of course, any cyclic graph does not have a topological ordering, so we treat sequential components as a starting point and split the graph along their entering edges. And as a bonus, any graph that is still cyclic after this split is invalid, so we can detect faulty models. So this brings us to SyncSim, which was the inspiration for Syncrim. SyncSim is a synchronous circuit simulator which was developed at LTU, my university, some 20 years ago. It's written in Java, and since the release, it's been used for teaching courses in low-level programming at LTU. So the simulator implements a model of a MIPS processor and is fully open source, but the development has pretty much stopped. And this is a picture of SyncSim. So in the middle here, now I could use the pointer, there we are. In the middle here we have the MIPS core, I guess. To the left is an instruction view, and we can see which instruction is executing. We can set some breakpoints, and we have a data memory view here, so we can sort of see output. And this screenshot, if I remember correctly, is taken on a 1080p screen, and you can sort of see in the view that the font scaling is a bit wonky, and this gets even worse on higher resolutions, which I think this is a 15-year-old Java Swing oddity, but I'm not sure. Right, so some pain points of SyncSim. Firstly, the toolchain we use to compile code for the MIPS model is an old fork of the MIPS GNU toolchain. So it's outdated and lacks support for operating systems like Windows and Mac OS. And this is important because we use SyncSim for an introductory course in assembly programming at LTU. So each year, something like 100 students are using this, and some of them have never touched Linux, let alone a terminal. So assisting them with setting up the environment for this on 100 different setups on each course occasion and staying sane at the same time is borderline impossible. Also, the MIPS architecture, while it's a good entry point for teaching assembly, it's not exactly state-of-the-art, to the point where even MIPS Technologies, so the company behind the architecture, has moved on to designing RISC-Vs. And as I said, SyncSim is about 20 years old at this point, so the people behind the project have also moved on. So there is there is little documentation, so the project is effectively unmaintainable. And because of this, SyncSim is stuck with the MIPS and this 15-year-old wonky Java Swing version. So how do we address this? We thought we can just rewrite it in Rust. So now we get to SyncCrim, which is the topic of this presentation. And it's well, basically intended as a successor to SyncSim, but written completely in Rust. So instead of the MIPS, we bundle this simulator with a model of a RISC-V core and some generic components like the adder or the register I showed in the simple circuit. This time around, to compile the user-provided code, we didn't want to rely on some external tool chain. But how can we do that? Essentially, the RISC-V model memory is initialized using an ELF binary, which we disassemble, and we populate the memory with the data and the instructions contained within. But to get an ELF, we need a compiler, so we are back to square one, RISC-V GNU toolchain. It is, or is it? Since we are running a Rust crate, the Rust toolchain is already there, so we thought we can use that instead. We can package the RISC-V model with a dummy crate, move the user-provided code and the linker script into that crate, compile it using the Rust toolchain, grab the resulting binary, and just populate the model memory using that. And all of this is done with a single command from the user and just the Rust toolchain, so we don't need anything aside from that. And my takeaway from this is that for a simple user space application like this, we don't really care about the memory safety features of Rust. Instead, we have Cargo managing a dependency tree with like 400 library crates, and Rust C cross-compiling for the RISC-V target out of the box. So the productivity boost here is pretty massive. Oh, and this picture shows this is basically the entirety of that dummy crate. So here all we do is we emit this assembly file as a global assembly block. And we also have to provide a panic handler to satisfy the compiler. But since we never call it from the assembly, it's optimized out. Right, so now I'll hopefully show you what running SyncSim or SyncCrim looks like in practice. And for this, I can escape. right. Yes, so it's just cargo run. We point it to the RISC-V model. In release mode, we give it an assembly file and a path to the linker script. And here we have it. And it's much the same as SyncSim. Let's see if I can zoom out a bit so you can see the model. Ah, it's a bit sensitive. Sorry. Yeah, maybe I'll just move them out of the way and you sort of get the gist. So it's kind of like SyncSim in the GUI department. You have your instruction memory highlighting which instruction is executing. You have a data memory and a view of the registers. And if we, let's see if I can find the end flag. Is that it? I hope so, yeah. And we run the simulation. After a while, we can see that there is some Shakespeare output in the data memory. This is a kind of an infamous lab at the LTU, which I ported to the RISC-V. Let's see if I can find the slide. Start from current, yes. Now, as far as the GUI goes, to address the stuck with Java Swing issue, we chose to completely decouple the simulator backend from the front end. And this allows us to experiment with using different GUI frameworks without changing the underlying implementation. So at first, we were focusing on a Visia-based interface, but since then, I've personally moved on to using eGUI, which Per was using for his cut creator crate. And my takeaway from this, at least, is that it seems using Visia, it's easier to get exactly what you want, while eGUI provides a quick way to get somewhere in that ballpark, and you can just move on to other issues, which is nice when you're just trying to get it out of your way. This decoupling of the front end and the back end also opens up a possibility for running in headless mode, so without the GUI. And I'll talk about the possible application for this later. And we also provide a graphical way to design models with an editor, so I think it's a quick way in to just start experimenting with the tool. And this is a screenshot of this editor mode, so you can sort of drag. It's in horrible resolution, but you get the gist. You can sort of drag the components in from the left side into the view and connect them with wires. And there is, of course, also a way to do this programmatically if you don't like the GUI. So, although the use case for SyncSim has mostly been education, there's potential to go beyond that with Syncrim. If we consider the RISC-V architecture, we have an open ISA, which allows smaller companies to manufacture their own cores with custom features. But prototyping these takes a lot of time and effort. So tools like Syncrim offer a much higher level of abstraction. Components can be implemented and integrated really quickly, so there is room here for some hardware-software co-design experiments. As an example, we have the Click, which is an interrupt controller. And to give some background, if you're familiar with embedded Rust, you might have heard of the Arctic framework, maybe, which is essentially a real-time operating system, first developed at LTU, but now it's more of a community project. And it's widely adopted in the embedded Rust community. So Arctic leverages on the Cortex-M interrupt controller to accelerate scheduling of tasks. And because of this, it's incompatible with RISC-V microcontrollers. When exploring ways to port Arctic to the RISC-V architecture, we quickly came to the realization that the interrupt controller, or the standard interrupt controller on the RISC-V, is too primitive to support this Arctic acceleration scheme. There is a specification out there for an architecture extension called the Click, which solves the issue, but it's hot off the press, so there's no actual microcontrollers packaged with the Click. So instead we decided to implement it for the Syncrim RISC-V model, so we could start exploring how we would port Arctic to this emerging architecture. And so implementing this component took like a couple of days, and now we have a Rust click driver and an Arctic port ready for testing for when reality catches up. And actually last evening I found this really obscure Chinese manufacturer that are claiming they're packaging their chips with a click, so maybe I'll order that and we will see where that goes. We have. The same company has made a fork of QEMU, which implements this obscure chip, which I was trying to get to work yesterday, but I didn't quite finish it.
Excuse me, here's a microphone.
Yes, sorry.
Here's a microphone for questions, just reminding you guys. Thank you.
So the question was, which company? And it's T-Head. So it's a subsidiary of Alibaba, and this you might have heard of. Right. Another example is Antic, which is a hardware-accelerated priority queue proposed by Antti, who's here somewhere, I think. Yep, over there. And it allows for constant time push, pop, and drop operations, which is interesting for us Arctic folks, because we use timer queues to schedule future tasks. So during the fall, Antti visited us in Luleå for a couple of days, but the issue at the time was that Antic had just been presented a week prior, so there was still a long way out to having a real core integrated with it. So during his visit, we implemented an Antic component for Syncrim, and we could start playing around and exploring what could be done with it. Right, so when Per first presented Syncrim in Helsinki in June, I was unfortunately not present, but I know what it looked like. And at that point, it was about a month old and just had a bare bones Visia GUI and some proof of concept examples. So in other words, we've come quite a long way since then. We now have a working and tested RISC-V model and a decent, I would say, graphical user interface. But there's still a lot to do. The headless mode I mentioned earlier is not implemented, but would open up the possibility for integration of Syncrim models with CI. So you could use Syncrim to simulate architectures which you don't have QEMU models for. So, for example, this click-equipped RISC-V. And in this case, a debugger component would be of use. So you could connect to the simulated core using GDB. And I have a proof of concept for this, but not much more. And of course, we want to add more models. There's just never enough. So to wrap this up, the project is fully open source and available on GitHub. So go on and check it out if you're interested. And please use this branch. It's the most up-to-date, so this eGUI inst data. And thank you for listening. And do we have any questions? So we have over there.
You were mentioning about the potential applications of the headless version. Have you thought about using it like for the recent validation projects that have started for validating the CVA6 and more? Like, do you think these could be used to simulate like high complexity
I think
models?
Yes, probably, but then you would sort of need to port the model to this new framework, and of course there can be error in between. There's no way to generate these models, so that's like another.
In your example code, you use assembly directly included to the binary.
Yes.
Why don't you use RISC-V RT crate? Is it incompatible with the platform or what?
Why I don't use the RISC-V RT crate? Well, that's a Rust crate, and so the example was just an simple assembly example, but we do run Rust crates using the RISC-V RT crate.
Okay, yeah, and the other question, I was a bit surprised that you only mentioned click, because from what I recall in the very in one of the first microcontrollers on RISC-V, there was already a Blick interrupt controller, which is more powerful and it has priority. So it looks like it can be suitable for Arctic, for example.
Yes, and there is a way to map Arctic to the Blick, but it's sort of complicated and I don't really remember what the issue was there, but maybe Per knows this off the top of his head. Do you?
I'm actually an expert on this particular subject, but I don't recall either.
Henry also knows this, probably.
Do you have any idea? No, you can go ahead. I don't remember. I think Blick has it has the threshold register and it has priorities. And what else do you need? I think there was a third thing that we also need.
We wrote a paper on this, on mapping Arctic to different interrupt controllers, and the Blick was feasible, but there was some caveats, I think. I don't remember.
I don't think we targeted the PLIC in the paper. I don't think we analyzed it in depth.
But my understanding is that it's intended for multi-core usage and that it's not really a local interrupt.
Okay, I remember now. So the PLIC, what it usually does is that it multiplexes a bunch of external interrupts to a particular core. So I'm not sure if it I mean, from the hardware point of view, I think you effectively have one interrupt and then I'm not sure if you do software dispatch or whether it delegates to CLIC to do the rest of the processing, but I think the PLIC operates on the wrong level in some sense, but we'd have to take a look at the spec and revisit the issue.
And maybe could it be that the Blick doesn't support raising interrupts programmatically, so you can't set the pending flag from your software, which sort of ruins the idea of software tasks if you know how those work in Arctic.
I think it was a little unclear in some of both the CLIC and the PLIC specification. I think it was sort of left unsaid if you can raise them because it's.
Well, in the Click you can. It's sort of.
Okay.
Yeah.
So at least on ARM platforms, it's like given that you can raise any interrupt from software. Even hardware interrupts, you can raise them from software, which is of course useful for testing and for, I guess, delaying the dispatch of an interrupt or something like that, or like delegating to software or whatever. But on RISC-V, it's not always like that.
Yep. So I hope that answers your question a bit at least. Any other questions? Yes.
Does the CPU model in the simulation work on the kind of gate level simulation, or is it like a separate block that's hard-coded to just magically do something within the Rust and then produce the values for the next iteration?
Maybe I can show if I close out of this. No, not out of LibreOffice, but Syncrim. Yes. If I LVM here, let's see. Components, and let's see if we can find a simple one. Maybe actually maybe the register file. So basically this is one of the components, so this is the register file. And so you have some internal state, some input ports, and then there's some output ports as well. And all it does is sort of implement this component trait, which consists of a single, or pretty much a single function, which is this clock method, which is called by the simulator on every clock cycle. And so what it does is sort of get its inputs, do some Rust magic to calculate the outputs, and set the outputs. So here we, I guess, check the right enable, we check the right address, we modify the state, we see if there's a read or a read address, and we set the read output to the sort of requested register. Does that answer your question?
Yes. I also have a follow-up question that's somewhat related or not. I've been also playing with the idea of these simulators, but never got to finish any of my ideas. But one idea would be that if you get like a really complicated model that has plenty of ports and it gets slow to simulate, then you could basically double buffer every wire in there and then just accelerate with the GPU or something. Have you thought it would? Then you wouldn't need to figure out the order to evaluate or anything like that.
That it needs to.
So it would kind of evaluate every block in parallel and then get the next state and then just double buffer that. Have you thought about it?
Yes, we've been sort of discussing this, but we haven't really done anything in that direction.
I can just comment a bit. The idea is that it's completely up to you at what level you want to model. The register file here is modeled at the RTL level, but you can also hide internal state. So if you have something that is really, really complex, you might implement the state machine and so forth directly in Rust and just have a sort of a high-level model of your underlying hardware. Enough for doing simulation, but it's not really reflecting the exact internal state updates that you might have in an RTL model of it. Or at least you're hiding it from the end user. And since we are using Rust, and Rust is fairly good at optimizing code, we haven't seen any performance issues. It's more like the performance issue is more about the usability and the graphical user interface. And we haven't, this is not intended, at least for now, for running Linux inside of the simulator. That's not our target. But at least to be able to evaluate like this architectural extensions, it's very, very fast to come up with a new extension or a prototyping. The click was a couple of days. Yep. Prototyping Antic was also just a 2-day effort. So in comparison to writing HDL code for the same thing, I think this is much faster. And you can directly run program against them. Otherwise, you would have to do some very later interaction, and it's not so easy to simulate software onto very later as it's to do it here. Yep. So I think that maybe gives a bit of background to what the intentions are. But since it's an open source framework, and this is truly open source with an open source license to it, so it's just for anybody to.
I don't know if we've actually decided on a license, but it will be free and open source.
Yeah.
And all
it
of
is
that,
open source, but and it will be free, so it's not contained in any way. Yes.
You were showing the code just now, and so you're passing the mutable simulator through to every call and so on, and you're doing like get input value, set input value kind of things. So what is kind of the heap structure of your simulator, or when you are getting a value for your input, or when you're writing your output, where is it actually kind of stored? What kind of structure does the simulator hold for it?
That's a good question. Don't remember. It was a long time since I touched the actual simulator backend. Let's see if we can.
As of now, we have been experimenting a bit with how to do this, and this is a very quick and dirty approach to it. The simulator itself holds a global state. So everything is just stored as just U32s. There is nothing else. So there is no typed data inside of the simulator. In the next revision, we might look into instead letting the components host the data. And that would allow us just to use a trait for getting and setting in a more controlled way, meaning that you could not accidentally connect the wrong typed port to, well, it will be a type error if you try to do something like that, because then we would have a try into and it will fail. So this is not done, and the proof of concept state that we have now is sufficient for our needs, but we are always looking for improvements.
So the global state, how is it actually? Is it just like a hash map of the
I think it's a hash map.
Yeah.
Yes.
So this is currently just a simulator. Have you considered maybe adding possibilities to do like a hybrid approach of like maybe grabbing a logic analyzer and a physical chip and put some leads on some lanes and analyzing or simulating or doing a combination approach of software and hardware?
I don't think I follow. Can you?
So would it be possible to step through some things on actual hardware and visualize it with the simulator as well, or do a sort of combined approach between hardware and simulation? For example, you have the component model here so that you can have these inputs and outputs. Could you, for example, add some hardware components where that signal goes to and then comes back to your simulator?
Yeah. Or comes back to your simulator. We haven't really thought about it, but it would be possible. Yeah.
Okay. Yeah.
Once again, I can comment a bit about this. We did something similar when it comes to SyncSim about 10 years ago, or maybe it was more like 15 years ago. We had a simulation toolchain running in parallel, in tandem with SyncSim. So we were interacting with that in order to have HDL models that were simulated, co-simulated with the SyncSim module or models, and allowing like visualization for actual HDL. But we dropped that because our Europractice sort of contract went out, and it was very, very expensive to get these mentor tools at that time. And I think now with tools like Verilator, it's probably feasible again. I haven't looked at interchange format in between, how you would interact with a Verilator. Because Verilator does some things very good because it starts from real HDL. Here we can, as I mentioned, abstract further if we want. Yes, sorry.
Great. So we'll be switching the speakers to the timetable, and for that we'll have a short technical break, apparently just a couple of minutes as we rewire the next person. So I think it will be Vadim next, right? So you're up.
Thank you for the questions and for listening.
And while the speakers are setting up, I have some extra special questions due to tradition to the audience. So since the beginning of the meetups, I think we've had this tradition of asking this pattern of questions that should be familiar to most of the people who go to the Rust meetup. And I think the first one is usually something along the lines of, so we answer the question by raise of hands. So keep your hand in the air for a while, look around. The first question is, how many of you have used Rust for a work project? Then we have the follow-up question to that, which let's start. Okay, so so for the first 10 or so meetups, it was only just me raising my hand, and the funny thing about that was that it's like it wasn't like a real job because it was for the university. So like that was like a big sort of talking point back then. And No, not a real job. But actually, I think quite a lot of the people here who are raising their hands are doing some research project or so. Is there anyone who would consider that they might be using or want to share that they might be using Rust in production or something similar to that? Okay, so we do actually have like 6 or 7 or 8 even hands. So I think like maybe 1 year ago I think there was 1 or something like that. So things seem to be changing. Was there any other of these questions? Does somebody recall any hobby projects? Yeah, well, I for sure have done some hobby projects in Rust. Yes, that's almost everyone, unsurprisingly. Yeah. So how's our tech coming along? Are we close to ready?
Yep.
Okay. So that's an interesting question. So before we go into that, I actually want to briefly mention that during the last autumn, I ran a new course at the university called, well, the new name is Dependable Embedded Systems. And on that course, we explored how do you implement dependable embedded systems from many points of view. And one of the interesting things that happened during the course was that I think the Ferrocene company came out with the first version that is, I believe the term for this would be this of the compiler, that it is formally qualified. There's 2 terms. Right. Certified for used. Yeah. So the idea is basically that it's the first gate that you are allowed to go to the authorities that this might be a compiler that you can use for a high in a like a high reliability context. It's the Can you try it with the microphone? I can't.
So this certified compiler is only really relevant for the target code, the code which actually runs on the production device. Your testing code is a different thing. That can be done in Rust even before we had this, because that does not need the certifications usually. Well, there are some exceptions, but usually it doesn't.
So with that, so there was somebody in the audience who was interested in knowing if a company is interested in using this language in a setting where something like this would be required, like the certification of the compiler. So a raise of hands for if anyone's using Rust in a like a high criticality setting, let's say. No one at the moment, but maybe next year. So hopefully, yeah. That's that for my interlude. So thank you.
Okay, well, I will continue then. I hope you hear me on the backsides. So today I will be talking about USB libraries we have in Rust, which are mostly about USB devices and embedded USB devices in particular. And well, maybe my first question would be, how many of you made any USB devices? Okay, quite a nice amount. So for the rest maybe, or like in general, I will go through some USB basics on a single page, but yeah. So USB is a relatively simple protocol. It has USB hosts and devices concepts, and hosts are kind of the main component here, which initiates all the transfers, and we also have USB hubs to multiply the number of devices we can connect to a single host. And also USB has some terms like device classes and composite devices, and composite device is usually a device which contains multiple classes, and the class may be anything like a human interface device, which is a keyboard or sound card or flash drive or whatever. So you may have multiple of them, especially if you have some complex device like an SD card reader plus Ethernet plus HDMI or something. So here things go more complex than usual. And on the very basic level, communication is performed via so-called endpoints, which are kind of sockets in a way, and we have a limited number of endpoints in each device. So when hosts want to send or read the data, it communicates to a specific endpoint of a device which is numbered. And a good thing about USB that it tries to simplify and to reduce the amount of data we need to transfer, to simplify protocols, and it achieves this by separating descriptors and raw data. So most USB devices communicating beforehand or over some like generic protocols what they do support, which is called descriptor, and then when the host needs to communicate to the device, it uses data of a known protocol, and it doesn't have to support complex things like TLV or JSON or whatever else. So descriptor basically tells what to expect from this device and how it is supposed to be used. And on the physical level, USB is just two lines, at least up to high-speed USB. It's just D plus, D minus, half duplex, which basically means that you cannot send and receive at the same time. So the overall bandwidth you have is divided between in and out transactions. And we have different speed grades, like low speed, which is, I guess, extremely uncommon nowadays, and I don't really know if there are even devices on sale. And there are full-speed devices, which are most microcontrollers, if they support USB. There are high-speed devices, which are like high-grade devices at this point, like flash drives, which require more speed, or Ethernet things, and some microcontrollers as well when they have a lot of capacity. And yeah, nowadays we have also super speed, which is even faster, and there are multiple ways to do it. So overall, the USB communication works on different levels of abstraction, and we have this highest function layer, which, like, for example, a disk device which has communicated to it as a disk or as sector reads and so on, and then we have lower layers, but the actual communications happens at the lowest layer. So all the transactions between different layers are just translated by software. So in the end, you have only these bits on the wire. And well, from these bits, it may be really difficult to tell what's going on because you need to know the whole protocol from the bottom to the top. But this simplifies everything. So when we develop USB devices, we are mainly interested in the lowest layer, because if it works, then you can do everything. And as I said, USB communication is doable via USB endpoints, and each device may have up to 16 endpoints in each direction. So if you need something bidirectional, you need to use two different endpoints. And endpoints may have different types. So the most basic type is control endpoint, which is also used for device information, for descriptor getting, for some control to turn off or reset the device or something like that. And it is also used for some functions, for really simple functions. And this is usually this DFU, which is even standardized. So this is device firmware upgrade and some other firmware upgrade protocols as well. And it is also widely used for custom vendor commands. So if some vendor decides to implement its own device, it may also use these basic endpoints because they're simple. Then we have bulk endpoints, and bulk endpoints are often used in situations when we need reliable communication, and when, for example, some request fails, we need to retry this request so the data is not lost. And like the most common example of this is flash drives. These are using bulk endpoints. Then we have interrupt endpoints, which are mostly used for some slow polling things, and for example, for keyboards, mice, gamepads, which just report that some buttons are pressed or released and so on. And then we have the most complex thingy, which is isochronous endpoints, which these endpoints are used for predictable but not reliable communication, because when you want to make something really predictable, you can't make it reliable. And this predictability means that you always have some bandwidth, which is allocated in beforehand, and you also guarantee that the requests will be executed at the same time compared to each other. So the latency will be roughly the same between requests. And this is important for some streaming things like web cameras and audio devices. Then we have Rust USB ecosystem, which sort of separates different concepts. And if you have a firmware which implements a USB device, then it often uses some HAL for an MCU, which is hardware abstraction layer. It implements some basic components like UART drivers, clock configuration, and so on. And USB-related components, and the most important component here is USB device, which is a central crate which serves as a base for both USB drivers and USB classes. USB drivers are MCU-specific components which know how to communicate to a specific USB peripheral and how to implement different types of endpoint transactions. And then USB classes know nothing about hardware. Instead, they know which descriptors to present and how many endpoints they need, how to translate data sent to these endpoints into something useful. So, for example, if you have USB serial, we translate all the requests on endpoints into some stream of bytes. And all the requests are packets, and since we are implemented serial port, we need to convert packets into bytes and vice versa. So this kind of translation happens in classes. And how it was roughly 5 years ago, we had USB device crate, and then we had one driver, which was for STM3203, and then we had one class, which is USB serial, and all these libraries were implemented by a single person, which is here. But what we have now the situation is much better. I don't know how this happened, but probably it was so good that people started to implement some drivers and classes. And device drivers cover quite a lot of popular microcontrollers. So we have 2 device drivers for STM32 microcontrollers, which has completely different peripherals. Then we have for NRF52. Then we have for the newest Raspberry Pi 2040, and so on and so on. And there are also a lot of USB classes, like heat class, which can be used for keyboards. There is even a complete project of a keyboard written in Rust, which uses this. Then we have classes for storage, have classes for this. Oh, we have 2 heat classes. Okay, good. Very useful class, yes, indeed. We even have web USB class, which implements a really interesting concept when you can control your USB device from the browser. Modern browsers, well, I don't know, maybe even Firefox nowadays support this, but this is really convenient sometimes when you want to simplify life for your user. You can just implement some website and then connect this website to your device. Implement automatic firmware update, whatever you need. And, well, it was surprising, but USB device has 101 reverse dependencies. So quite a lot of crates nowadays use it. These are project crates, hull crates, and these device drivers, USB classes. Yeah. And what it takes to make a USB driver, for example. I will just go quickly through these to make you understand roughly what it takes. So when you have just a microcontroller and you don't have a driver for this microcontroller, or you have your FPGA stuff, something that is not supported yet. So first thing you want to do is to make the host detect your device. Sometimes you may have a board where it is already implemented because you have a pull-up resistor or something like that. So when you just connect your board, host already tries to detect your device and shows some errors in DMASC, for example. But when you have a normal peripheral, you don't need to do this. So usually when you connect your device, host doesn't see anything and it doesn't track, it doesn't try to initialize your device or read something from it. So first you're trying to enable this peripheral and make it somehow be detected by the host. And then some basic things like USB reset handling happen, because USB reset resets the internal state, so it is important to handle it first. Then there is enumeration process, and enumeration process is more or less reading descriptors from the device. So you need to support endpoint 0, which is control endpoint. So this endpoint should provide some information. Usually all the information you need at this point is already provided by the USB device crate, but it should be somehow transferred to the endpoint on the lower layer, because USB device doesn't know anything about hardware. And here, like, an interesting thing to do is to try enumeration without any classes. So it's just an empty device which has PID, VID, things like that, like generic name. Because this way all the descriptors will feed into 64-byte packet. So it is a relatively easy task. And when you start filling this device with some classes, then it becomes larger and larger, and sometimes it just doesn't fit into the internal buffer. It happens. Then USB full-speed devices, for example, support 64-byte packets and 8-byte packets for this endpoint. And of course, if you set it to 8 bytes, then the whole report doesn't fit already. And you have to do something, so bugs happen at this point. Then there are truncated P0 transactions, like the host says, I want 64 bytes from you, and then after the first 8 bytes, it says, like, stop, I don't need anymore. This is a really weird condition. For example, on the NRF microcontrollers, it seemed that there is no good way to handle it, because, well, maybe creators of it didn't think thoroughly that this situation may happen. But Linux does this every time. You can trust that this will be broken if you don't think about it. And then when the control endpoints are more or less implemented, you can start implement all the other endpoint types. They're a bit different, so some type-specific implementation may be needed. And for isochronous endpoints, some complex synchronization may be needed as well, but this is probably lives in a class implementation. So on each stage here, you may face some bugs, and it may be really difficult to debug these bugs. So I'm going to discuss how to handle this. As for the debugging, we have multiple options. Some of them are free, some of them are not. But the most basic option as GDB is really useless, because when you try to debug something in GDB, you are usually setting a breakpoint or on something, and then when you set this breakpoint, then USB stops working. Because USB works in terms of frames, which happen each millisecond on slow USB and some microseconds on faster USB. So when you even stop for a brief while, the whole USB device most likely stops working after that. So enumeration fails, for example, and it will not retry. So garbage. Then we have Wireshark, and Wireshark is not only able to sniff traffic on your network card, but it also has possibility to capture USB requests. But the thing is that it captures it on the very high level from the operating system, and it is mostly useful when you have a protocol problem, not a low-level problem. So at the very first stages of development, this is quite useless. Well, but it is free. Then we have the most important tool here is logic analyzers. Logic analyzer is a dedicated hardware which can gather bits from your wires. And usually the thing is that you can store quite a lot of data before you analyze this data. So for example, logic analyzers, which I show later, these are capable of storing data in real time. So you can store as much data as you can fit on your hard drive or SSD. Quite unlimited possibilities. And this is quite important because in this case you see almost the full picture of what happens with your USB device. The only thing you do not see is what happens inside your device, but it's a bit different story.
Excellent.
So one software way to trace USB might be to use eBPF filters in kernel. So you can attach like basically for any symbol or kernel function these small eBPF programs that you can use like way more low latency to trace stuff such as USB traffic.
Yeah, so this might work, but again, I'm not sure if you will be able to gather enough low-level information because this information may disappear already when it enters hardware you are analyzing.
Okay.
Your PC, you may not see a packet because it is lost due to some CRC reasons, for example.
Okay.
So if CRC fails, you may not see it at all in the Linux kernel. So, well, I don't know. Yeah, this should provide better granularity than Wireshark.
Yeah, it's at least should be better than Wireshark.
Yeah,
even if not
should
perfect.
be better for sure.
Yeah.
By the way, do you know any tools which implement this approach already? Like easy to use tools?
No, I do Linux kernel professionally, so I just use this tool called BPS Trace when I need to debug kernel bugs. So I don't know. I actually checked like recently that there's a Rust crate that you can use to create these eBPF filters for the kernel, but I haven't tried that yet.
Yeah, but then you need to understand what exactly you want to hook. So this is already kind of low level.
True. That's true because it's like ever chasing target. Yes. Yeah.
But yeah, quite an interesting approach. At least it can be developed into a tool one day. I hope to see it. Yes. As for the logic analyzers, I think I have said everything. So. And we have another approach for trying to investigate what's going on inside the microcontroller, which is more or less tracing or printf debugging or whatever you call it. And there we have UART, we have RTT and DFMT. I will discuss this a bit later. So as for the logic analyzers, I'm not aware of all the logic analyzers, but these are probably the most common options apart from the last one. The first one is relatively expensive, but it is really good and it is capable of quite a good speed. So you will definitely be able to get all the USB communication with quite a good precision. And it also promised like 8 channels, but this is not completely true because with 100 mega samples per second, you can only sniff up to 3 channels. And if you need more, then the speed will be lower. Because everything is bounded by the USB 2.0 speed, which is not super great. But there are other options like Logic 16, which uses USB 3.0, so it should be faster, but it is damn expensive. I wouldn't recommend if you just need to debug USB. And most of the logic analyzers are based on Cypress FX2 chip, which is kind of data to USB stuff. It implements a FIFO in its basic implementation. And for example, in logic, we get data from pins through FPGA, and FPGA feeds some really fast stream of data towards Cypress, and Cypress streams this over USB. Have quite a lot of bandwidth there. And this device also supports ADC, so you can measure some analog signals, but the speed will not be 100 megahertz, of course, because that's even more data. Then we have clones, and these clones are quite good, and sometimes they are quite simple. So for example, the clone of the very old logic analyzer, which is just Celia Logic, it is cheap, and it provides like 24 megasamples per second, 8 channels at the same time, and based on more or less the same hardware, except there is no FPGA, there is no ADC, it is suitable only for digital signals. These 24 megasamples per second is maximum, and the problem is that this is what you really need for USB, because for USB is 12 megahertz, and if you go below that, you will not be able to capture any USB traffic at all, or at least decode it. And the problem with this is that if you have any web camera or some fast device like hard drive or something like that running on the same root hub, you will not be able to achieve this speed, because this speed pushes the device to its maximum bandwidth, basically. So you need a really, really free root hub in order to use it at the max speed. But, well, if you have a laptop, for example, you can connect a logic analyzer to a laptop and then everything else to a PC, something like that. Then we have Logic 16 clone, which is capable of 100 MSPS, costs a little bit more, and it has also 16 channels, which are also a bit fake because you cannot use all 16 at this speed. But still, you can use at least 3 at this speed for sure, and the idea is pretty much the same. You have the Cypress FX2 plus FPGA to handle different number of channels at different speeds. Then we have DS Logic. I don't really know anything about it, but it is a bit better in a way that apart from FPGA, they also have memory. So it is capable of streaming, or at least capturing streams which are much faster than USB. So it just remembers this data to memory at some limited amount and then reports this to PC. So it's just the same thing, but with a huge cache. And we have a specialized device which is called Luna, or it was for some reason renamed to Syntheon. It is capable of analyzing USB high speed, which is quite rare, and usually if you have a production device which is capable of analyzing USB high speed, it is really expensive. None of the logic analyzers above are capable of analyzing this USB speed. But this device is, so it is basically based on FPGA plus USB high-speed PHYs. And it has 4 USBs. I'm not sure if you are able to use all 4, but still for analysis purposes, 3 should be enough. Yeah, it can be currently pre-ordered on current crowd supply. I'm not sure if they are going to ship it, but the date which is set there is 31st of January this year. Who knows, maybe this will be the final one, but I don't know. Cannot promise anything because it's a crowd supply. As for the logic analyzer software, the situation is pretty poor, I would say, because we have official software from Celia, which is proprietary, but it can be extended with some plugins, like decoder plugins, which is not useful for USB in this scenario, but it also has a decoder for USB, and this decoder is quite bad, I would say, because sometimes it just fails to achieve a lock on the data it fetches, even if this data is fetched at the very high speed, like maximum possibilities, but then it fails to acquire a lock and the decoded data is just wrong. But it is capable of exporting to VCD format or some other binary formats, and these formats can be imported to the second software option we have. And this software option is open source. It's called SIGROC. This SIGROC is like a base library which supports multiple logic analyzers, and PulseView is a graphical user interface for it. So you can use it directly with the probes which support this which are supported by this software, for example, all the clones and some generic FX2 boards. And yeah, there is also an option if you want to use proprietary software for capturing, then you can export data from proprietary software and use it in the open source software. Not so convenient, but the second option works great for USB, and it shows you all the transactions in different details, so you can choose whether you need very low level representation or the highest level when you have requests. Yeah, also I noticed that the latest version of the official logic software for some reason doesn't support export into VCD anymore. I remember that 1.x supports, and I checked this, but 2.x for some reason doesn't support. It supports CSV and some binary format. That's it. But yeah, it can be converted, of course, into VCD or something suitable for SIGROC. And then we have tracing. There are multiple options in the Rust ecosystem. The first one, the oldest one, which is called semi-hosting. Semi-hosting is a mechanism to fire an interrupt or a halt instruction inside the microcontroller and let the debugger grab the data to the outside world. Semi-hosting is quite good in a way that you can work even with files on your host PC, but from the microcontroller. But it is really, really slow. And if you try to just send some bytes over it, it will be super slow. It is not suitable for debugging of USB, and I would think that with modern approach, you shouldn't use it at all and don't let anyone use it. Like friends don't let friends use semi-hosting. Then we have UART, which is quite a simple approach. You just send some bytes to it. But UART is slow, but this is not the main problem because the amount of data may be not so big. The bigger problem is that sometimes you need to send a lot of data, but in small chunks. So you have spikes in required performance of your CPU. And this is a big problem because often drivers are quite simple and a lot of CPU power is just consumed to send in bytes towards UART. Unless you have DMA or something fancy like on NRF52, which can send something transparently out of the UART, this will not work. And then we finally have RTT. RTT is a thing, I think, which comes from J-Link adapters, and it was initially for the C language, but in the Rust ecosystem we can have named things. So this may work with any adapter, not only J-Link, but whatever you want, like ST-Link, and with Rust, of course. The idea behind RTT is to offload data transfer to the debugger. So instead of sending something to the peripheral, like in case of UART, you just store this data in memory and wait until debugger grabs this data. But you don't wait right away, you just wait asynchronously when there is no space, for example. Or you can discard all data if there is no space. There are choices. But the most important thing is that it doesn't wait until the whole package is transmitted to the outside world. Instead, you connect your debugger to the chip, and this debugger polls your memory, polls your ring buffer for this data, and grabs when there is something new in this ring buffer. So this is really cheap, especially when your chip supports reading memory without stopping the core. That this is the main way you can use it efficiently, actually, because if you stop the code for each transaction, then what is the difference? And, well, this works, but this still requires some CPU cycles for formatting, especially if you have floating point values for some reason in USB debugging, then this is terribly slow. So people invented DefMT. DefMT is the idea of having formatting implemented on host instead of the device. So rather than formatting your format string on the device, you just send pointers to this format string and send all the data required for formatting, but don't do the formatting itself. This is even faster, but this requires some tooling on the outside of the firmware. And, well, this is doable. This has some problems sometimes when, for example, protocol version in the firmware doesn't match the protocol version of the software on your PC, but still, if you really want to use it, you can use it, and this is quite convenient way to debug and also the most efficient so far. What about testing? So, for example, you implemented something already. It kind of works, but you are not still sure that it works fully. Or, for example, you have a driver and someone makes some modifications to this driver, and you want to make sure that it still works correctly in all of the cases. So regression testing is the #1 goal here, especially if there is a driver that supports multiple microcontrollers. If you add support for just one new, you still have to test all the others. And also for peripheral driver testing in general. So if you add something, some functionality to it. But what is not covered yet is class testing, because different classes are different and it's quite difficult to arrange some generic way of testing classes. So in general, I suppose that whoever implements a class, they are responsible for testing this class at least on one microcontroller to make sure that it works somehow. The first thing we can use here to test our USB device implementation is the test class, so-called, provided by the USB device crate itself. This class implements multiple endpoints which are only used for testing, and it consists of both the firmware side and the host agent side. The firmware side is simplified to like 2 function calls, I suppose. The first one is to create this device and another one to poll this device. Quite simple to implement for any hardware if you have enough support for USB there. And the host agent is an application which runs all the tests. And there are a lot of tests there. So, well, as I said, yes, we allocate endpoints of all the different types to verify that they are successfully allocated, that the parameters of these endpoints are the same as supposed to be in the device implementation. There are also string descriptors which are tested not only for different interfaces, but also, I think, for different languages, because USB supports these, why not to test it? And there are also transfer testing when we send data towards endpoint or receive data from an endpoint to verify that data transfer works, and also different corner cases for transfer sizes are checked, which is very important because it may work, for example, if the packet is small, but then break if the packet is large enough. And also it measures bulk transfer bandwidth. So this may be useful to see if you have any performance regressions, for example. You can measure this bandwidth before and after the test. And also useful to compare it to the theoretical maximum, which is provided in the USB spec. Then we have quite a simple interrupt test, and the reason behind this test is that sometimes interrupts are not handled properly. So when interrupt happens, you can call a function to handle this interrupt from the library, but then it will not handle it completely, for example, because implementer forgot something about different interrupt aspects, and this interrupt will fire again. And this test basically tests that when we first upload the firmware to the device, the interrupt doesn't fire more than 10 times in a row. Because nothing happens, it shouldn't fire constantly. And then there is quite an interesting test, just a serial benchmark, but it is a stress test in a way because it tries to send as much data as possible toward the device, and device acts like a regular serial port, but it echoes all the data back, but in uppercase. These tests may not be trivial for the initial implementation because sometimes multiple requests may arrive one after another, and sometimes due to some bugs you will not be able to handle one of them, and then the whole packet is lost. So this test also verifies that all the data it sends is received back correctly, so no lost packets there, and the data itself is as expected. This test catches quite a lot of bugs. It's amazing how a simple test can find so many bugs. Then we have an interesting story. For some reason with this test, USB 3.0 ports lead to worse performance than USB 2.0 ports with the same device, with the same firmware. The reason is that as all the transfers happen within one frame, and one frame for slow devices is 1 millisecond, within one frame and 64-bit transfers, you can have only 18 transfers. And USB 3.0 ports use different polling pattern. For example, USB 2.0 ports for this test use like read, write, read, write, read, write. In this case, microcontroller is able to handle all the packets because all the writes arrive with some gap between them. But with 3.0 ports, some write operation can happen right after another. And in this case, if double buffering doesn't work or it is not implemented fully, then one of the write operation will fail. And due to the nature of USB, it is more expensive to fail a write operation toward the device than to fail a read operation towards host. Because during read operation, there is a small request which says, I want to read, and then you said, I have no data. But when you do write operation, you write all the data, and then microcontroller says, no, I cannot handle it. So you waste all the 64-byte packet just because microcontroller is not able to reply at the very beginning. That's how the protocol works. And in this test in general, in one frame, around 1 to 2 out requests just fail with this NUC because microcontroller is not able to handle this amount of data. Another reason with USB 3.0 that some bugs manifest only with these ports. For example, current implementation of USB OTG with high-speed devices, it just fails the test completely when you plug the device into 3.0 port. Works fine in 2.0. There are some bugs. So my recommendation here is if you're trying to debug your device and to understand why something doesn't work, plug it first to the 2.0 port. If it works there, then yeah, this is a separate story, but it would be much, much easier to reproduce a bug if you will not face any additional problems related to 3.0. But of course, when everything is ready and you want to do additional testing, then you can use it. It will introduce problems for sure. And then we have the final test, which is called Official USB Compliance Test Chapter 9. There are some other chapters as well, but this is like the most generic and it applies to all the devices. So you can plug your device and then run all the tests. And the most important thing about this test is that it checks all the dark corners of the USB stack. Well, not not all maybe, because there are some class-specific issues which can be found, of course, but at least if you forgot something which is really rare or seems to be unimportant, it will find it. This tool runs only on Windows, and it generates a nice test report, and if something fails, most likely it will say why it failed. And if your device is really, really bad, like a programmer based on a RISC-V chip which emulates FT232, then this programmer USB device may even crash this compliance test. That's a nice thing. I've never seen the device which is so bad that it not only fails, but it crashes the test software. For some reason nowadays it is really hard to find a 2.0 compatible software on the official website. It was there previously, but nowadays they are at 3.0, and this version for some reason just doesn't work with all devices and like simple devices based on microcontrollers. So good luck finding an old one, but you can mail me, I will send you an exe file. Another important thing about this test is that it interacts with the device on a very low level, and in order to achieve this, it hijacks control over the root hub. And when it does it, basically no other devices work on your USB root hub. And if you have a simple computer set up with a USB keyboard and a single root hub, then this USB keyboard just becomes disconnected. This is not a fatal issue in a way, because there is a safety startup procedure which allows you to roll back everything. If you do not press the button, OK, now everything works, then it will just disconnect from the root hub and everything starts working. But it is indeed an issue when you want to use this tool. So the only way I think to use it on a regular PC is to have multiple root hubs and somehow know which root hub corresponds to which port, and then use only this port for testing and only this root hub. But another option is to use a laptop, because often laptops implement PS2 keyboards or their emulation which are not USB keyboards, so at least keyboard works after that, or touchpad or something like that. Yeah,
I think an easy way is to use remote desktop.
Sorry?
Remote desktop. So you connect like remotely to your Windows machine.
Yeah, that's an interesting point. Yeah, good point.
No USB required.
Yeah, but then you still need two PCs. But yeah, this is possible.
Yes,
for sure.
but that's not. Nowadays, having two PCs is not so uncommon, I think.
Yeah. So yeah, this tool is nice, but there are some limitations, and sometimes it is difficult to use it. That's how it looks like. There is a window and there is a list of tests. By default, all the tests are selected. You just run the test suite and it reports something. So it marks a test green if it's passed, it marks a test red if it's failed, and so on. All the test suite is passed like in a minute or two. There is one test which is really long, which does like 200 enumerations in a row to verify that your device will not die after this. But yeah, this takes quite a while. But all other tests are really simple in a way that they are fast. So you can iterate testing again and again. Yeah, but everything is good, but what's next? So testing complex device drivers is really tedious. So when you have a driver which supports multiple microcontrollers or multiple peripherals, and you want to add another one, then how to test that no regressions happened. For example, the biggest driver, I guess so far, this Synopsys USB AutoGAA, supports 8 peripheral versions and 3 PHY types. Internal 1, internal 2, and external PHY. And you need to have all the hardware, ideally, to make sure that it still works. But at least some tests can be automated. So for example, USB device test class is a completely automated test. If something fails, it just returns an error code, and that's it. Then serial benchmark can be automated too. I'm not sure if it fails, if something goes wrong, but it should be really easy to make it fail. And then we have these chapter 9 tests, which are just bad because it's a Windows program. You cannot run it on Linux and so on. So there are some ways to improve. The first way is to test multiple devices roughly at the same time by just switching between these devices. They already have a prototype for this idea, which consists of a switch and control board, which is sort of a main board into which daughter boards with MCUs are inserted. So these boards implement switching.
We are starting to run out of time, so yeah, I mean,
like to start. So the idea is just to switch between these devices, and on this specific board, the switch is implemented in a way that only one reset is deasserted at the same point of time, and all the other signals are just combined. For slow USB devices, it should work, and in fact it works. And then you test one device and then deassert another device and test this device and so on. Just run all the tests in a loop over all the devices. And then it would be a really, really good idea to implement all the chapter 9 tests as a separate device, or at least as a software component, which can run these tests on Linux or somehow automated without any need to press buttons and so on. This requires, of course, some reverse engineering, and host implementation is needed if we need to implement this as a separate device. Yeah, but that's it. I wanted to tell you, so if you have any questions, please ask.
Yeah, I think we'll take the questions later on, and let's get the next presenter on the stage. So I guess we.
All right. While we set up, jump up, stretch, move your hands a bit. So I'll already start talking to get everything, myself and you included, warmed up. So I'm Aapo Alasuutari. I work as a TypeScript JavaScript programmer. I don't write Rust or I don't make money with Rust. I don't turn Rust into money. I barely write Rust. I'm pants at it. I'm very bad at it. I'm not going to show any of my code, and it's not because I don't want you to see it. It's horribly uncomfortable to show it to people. Like, look at this. It's great. No, it's not. But it's loading. Yeah. So earlier we mentioned that, or Henry mentioned that we were going back to the kind of traditionals of Tampere Rust meetups, which was embedded devices. So here's the other. Now I'm already making myself a tradition. So this is now a JavaScript conference. So we're going to be talking about building a JavaScript engine. This particular engine is called Nova, and it's a DoD, so data-oriented design-based JavaScript engine. So what on earth is Nova? It all starts with a joke. So a bunch of Dino enthusiasts walk into a Discord channel one night, and we're going to skip right to the punchline. So when are we starting our own JS engine? Now I need to pronounce this correctly. Andrew, no, that was wrong. Anyway, Andrew asked, and we started our own JS engine then. So this was nearly, what? Yeah, nearly 2 years ago or something. What? It's been a long time now. So we made some initial commits, started like a WASM engine. We bike shed the name, decided on, supernovas, so on and so forth. Space is very cool. Started working on the JavaScript engine structure, started our own parser, made a PR to start actually working with JavaScript values. It was based on the GC crate. If anyone has seen this particular Rust crate. So this was always written in Rust. I didn't actually mention it here, but yeah. GC crate provides reference counted GCable heap allocations basically. And with an it's not reference counted, but traced. And it has an automatic derived GC implementation, so you can kind of very easily set up stuff with it. And we also had a dynamic object trait. And then we removed the parser, started using OXC, the oxidation compiler, which is lovely. And then we just mostly did nothing until last summer. I then heard of data-oriented design or entity component systems from a friend of mine who works in gaming, in the gaming industry here in Tampere. And that piqued my interest. I started thinking, now that would be very interesting for a JavaScript engine. Now that is something. So Nova Engine today is a stack-based bytecode VM. So we use the oxidation compilers AST crate and parser crate to parse JavaScript code into an AST, abstract syntax tree. But then from that syntax tree, we immediately generate bytecode. We don't use the AST aside from that. And the heap design for the virtual machine is built in a data-oriented way. What that means, I'll talk about that in a bit. In horrible length. And the project structure is built around the ECMAScript specification itself. How many here have read language specifications? It's fun stuff. I've only read the ECMAScript specification. It's actually rather nicely structured. Like you can kind of read through it and see, yes, okay, that's how this works, and that's how this works. And why are you talking about that thing now here? It's why? Okay, whatever. It's probably the same for other languages as well. But the idea is that generally, if there's a section in the specification, we'll have a folder for that. If there's a subsection, then either we have a module or a subfolder for that, depending kind of on how deep the rabbit hole goes. And then when the spec starts to actually explain abstract operations, we'll have a function for that in the module. And the intention here is, of course, that this should be easy to understand for someone who has ever read the ECMAScript specification. It should be really easy to actually read one part of the specification and just start bashing out the abstract operation into Rust. And then, like, if the spec changes, if there are any updates or so on, we can just kind of take a jump from our implementation. There's already like a direct link to the specification. We can open that, see how it has changed, start fixing the issues. So, okay, that's what Nova Engine is, but what on earth is JavaScript? I mean, ECMAScript. So JavaScript is owned by Oracle, and it's just a name, trademark. So we talk of ECMAScript. ECMAScript is a dynamically typed language. In general, it then means that there is no information about what type a value is. Not when you're writing it, not when you're parsing it, not when you're compiling it, because you're compiling it. It's all only at runtime. And the type system itself is also, of course, needs to be fairly limited to accept this kind of unknownness. So there's undefined, there's null, 2 different bottom values. That's a great idea. Like, of course, how about we have like none, and then we could have like maybe. Would be fun. Strings, booleans, numbers, big ints if number is not enough for you, and symbol for magical things, and then object. That's it. Anyone spot anything missing? No floats and no functions. Yeah. So floats go into numbers. So the number in JavaScript is a double, except that it actually works differently with bitwise operations. When you do bitwise operations, it's a 32-bit signed integer. There's actually, I only realized or saw this like 2 days ago. ARM architecture, the processor has a specific instruction for calculating the JavaScript or the ECMAScript specs double to 32-bit signed integer operation. Okay. But yeah, so there are no objects because functions are objects. Aha! You didn't see that coming. No, yeah. So functions are objects. Arrays are objects. Array buffers. So that's like your normal vector. You would think like vector of U8s. That's an object. Everything is object basically. If it's not primitive, it's an object. So the ECMAScript spec then mostly deals and mostly talks of these values. And because the spec mostly talks about values, the engine mostly talks about values. There are some abstract operations which take as parameters, let's say, a string or a number or something. But those are specific cases where you know from the parsed code what is happening. But then when it's an actual like built-in function or something, it just takes values because it can be called with anything. Okay, so I'm going to quote quickly Chandler Carruth from 2014's CPPCon. Efficiency comes from operations or functions, and performance comes from data structures. So how does an engine actually implement a value is one of the most important questions that the engine needs to answer to then figure out how it's going to be performant. One option how to do value is do just like copyable value on the stack. So you would have some kind of massive thing that just can hold any type of value. It can hold any type of object and all the data associated with it, at least those parts that can be on the stack and like are not kind of must on the heap. And yeah, so the doing this, you would end up with a huge object or huge value because it always needs to be as big as the biggest value is. And you would need to have some internal discriminant in this data that knows, like, okay, what type of value is this? Another choice is to have a reference to your value be a reference to the heap. So your value is just a pointer. And then the heap is where your data is. Now your pointer, it can be typed, so its size doesn't change, and well, you still need an internal discriminant there on the heap. You can do some mitigations here, though, to maybe get rid of some of those. But that's another option. Kind of a rustier option would be to do an enum. So we do an enum with the payload being some kind of a reference to data on the heap. Or possibly it can be, of course, just stack data as well. And now if we do this, we might not require an internal discriminant in the data itself because we already have the enum discriminant. We could maybe kind of use that. Let's see. But there's one question, of course, is your payload, is your reference going to be a pointer? Or is it going to be something else? So how would a heap reference value work? This is how V8 does it. This is how JavaScript core also does it, basically. So the very naive implementation is to take a reference, and it's just a pointer, and the heap allocated value has that discriminant. V8 does something a little bit different. They do a tagged pointer. So their pointer contains a tag which tells, is the pointer actually a pointer, or is it actually an signed integer on the stack? And this is fairly simple, works well enough. It's well proven to be performant enough. It handles the most important special case, the I32, on the stack. And unfortunately, this means that only the heap knows what type of data you're dealing with. So when you see a value, you can check the tag to see if it's a small integer. But if it's not a small integer, then the next question you're going to ask is, what kind of data is this? That's a heap read. JavaScript core kind of does the same kind of thing, but they use a nan-boxed value. So this is Safari browser. So either their value is a valid double, F64, or it's not a number, in which case the 3 upper bits of the mantissa after the signaling bit contains a tag which then tells, are the bottom 48 bits going to be a pointer, or is it going to be some stack value like an I32 or something? This means that you can have full doubles on the stack. That's great. All JavaScript numbers basically are now on the stack. You can also probably put a lot more stuff into the 48 bottom bits that you get as payload. And you can discriminate the data a bit more on the stack with the nan tag. So you could have different kinds of pointers. Not just that, this is a pointer to the heap, but this is a pointer to a string. This is a pointer to an object, a pointer to a symbol, so on and so forth. You get 3 bits, so you can get 8 different values. But the downside here, in both of these, is that you're messing with pointers, mate. That's not good. Are you crazy? No. Unsafe and iffy. If you do any of this in Rust, you need to use the unsafe keyword. And we don't like that. Not here. Okay, we actually kind of do, but let's just pretend. Also the nan boxing, which kind of, if you look at it far enough, it seems to be the better one here. It's obviously getting more stuff onto the stack out of the heap. This breaks with 5-level paging. Intel is kind of pushing for that, I think, or at least makes it possible. And ARM is doing pointer cryptography starting from 8.3 or something. And that either of those completely breaks nan boxing. You cannot do nan boxing anymore with that because of how pointer upper bits are then used. All right. So this is a bad idea. Let's not do that. So let's go with the Rusty solution. Let's use an enum. So we take a Rust enum with a payload, and let's first ask ourselves, what is going to be the representation of our enum? Like, okay, we could just let Rust decide, but it's going to probably decide a U size for it. And that's a bit too much. We really don't need 2 to the power of 64 different variants. So no, thank you. The ECMAScript spec talks about 50 different types. And now I'm saying here type not as in JavaScript different value types, but just different kinds of objects plus all the primitives that you can find in the spec mentioned. So 255 should be enough. So we'll just use 1 byte as our enum discriminant. So then what about the payload? The obvious choice would be to use the pointer, but then our value is now 16 bytes. And 7 of those bytes are just filler, because you've got the discriminant, and you've got to get a pointer there. It's just empty there. That's horrible. No. We know the type of our value based on the enum variant. So can we then place the data for that type, T, into some arena that we can know, and then in a way kind of compress our pointers small enough that we could fit it in, or to end up with our value compressing down to 8 bytes. What kind of memory arena could we do? Well, a VEC. Yeah, sounds good enough. So VEC, that's a memory arena of type T, right? And one good thing, first of all, here is already that when you index into a VEC, the type or the index you give is a U size, yes, but it's not a memory offset into the vector. It's the index into the vector. That already compresses your pointers. Instead of you saying that, please take byte offset 2555 or something, you say, please give me index to 12 or whatever, and Rust will compute that automatically into a memory offset inside the machine, or the computer does it for you. So we don't need to store a memory offset. That compresses our pointer. That's nice, but also it's actually possible to just say, like, nobody's ever going to need more than 2 million items of any type T. So we don't need a U size. We can use a U32. So we use a U32 as our index into a vector of T, where the T is based on the representation or the enum variant. And our value just becomes a U8 and a U32. Stack knows the type of an item. It knows the index into a heap vector for that type. The way you access this particular data for this item is then to ask the virtual machine, you get a pointer to that thing, please give me data, or more like, please do some abstract operation on this value. Here's the type and its index. So it does it. Yeah, lovely. But can we do more? Is that it? No, we can do more. So we have about 200 discriminants left. That's plenty enough to do some fun things. So let's make a custom discriminant for I32. That's the most important stack case, kind of. What other things can we do? We still have 3 bytes that we were not using, so we can actually do U8 with 7 bytes of data, and this still fits in our value. So we can do actually an I56. Rust doesn't give us 56-bit integers directly. There is a proposal or RFC for this kind of magic, but I'm not sure if it would work here. But we can just do this manually. We just new type a 7-byte array. We can also do 7-byte short string optimization. So length, data, value, these sorts of strings that are very common in JavaScript. You get all of these on the stack. That's kind of lovely. Yeah, I'm digging this. Yeah. A future consideration also is that even if we go really crazy on making all sorts of stack-based data variants, we still probably have about 127 discriminants left over. So half the discriminant set is unused. So what if we just make sure we're never using the top bit of our discriminant, and we create thrown value variants? In JavaScript, when you throw a value, you can throw any value. Like it's not that you need to return an error or something, or throw an error. You can throw an undefined, you can throw a null, you can throw whatever. So if we make sure that we're never using the top bit of our representation value, we can essentially turn throwing a value into just setting its top bit and then returning it. That's kind of lovely. I like that a lot. Unfortunately, this means that our code, when we're writing it in Rust, we can no longer use the question mark operator. Like if you can't just do like an enum that has the question mark operator defined on it, except with the nightly try trait. And that, I would want to use that, but we're not using nightly, so we can't do that right now. Yeah. Also, the question mark operator is quite nice because it quite exactly matches what the ECMAScript spec uses. They use a prefix question mark to say, if this failed, then immediately fail it upwards. That's the question mark operator from Rust. They also use the exclamation mark to basically say unwrap. A future consideration is also like, can we go lower? We're currently at 64 bits, but could we go to 32 bits? That would mean that our indexes would be 24 bits. That's still probably enough values to run a decent JavaScript engine. Could we go down to 16 bits? So we would have 1 byte of the variant and 1 byte of data. So up to 255 indexes. We're not using the 0 value there for reasons. That's not a lot of values in a virtual machine, because this now means that there can only be 255 objects or numbers or strings in existence in the virtual machine at the same time. And if you go over that, then it crashes. But that would be a very small virtual machine. That would be quite fun. Also, our value currently lacks lifetime. That's not really great. You can grab a value, put it on the heap, and use it hours later as if it still worked. No, the index is going to be reused probably by this time. So we need to generate actually unique lifetimes for our agents or heaps. This requires some work, but also if we get the values tagged with a lifetime and we get the heap tagged with the same lifetime, we could probably write our heap GC, garbage collection algorithm, in such a way that the borrow checker actually starts helping us do GC correctly. Because if our GC algorithm is written as, I give you a heaped, generation lifetimed item, you return me an item of the same type with a new lifetime that I give you as parameter, then you basically are forced to do that transformation of from old lifetime to new lifetime, and we're just going to essentially be assigning your given value to the place where we got the old value from. So that would be kind of nice. Okay, so what's this got to do with data-oriented design at all? Like, and what is data-oriented design. I'm not an expert. I have, like as said, I heard about this stuff like last year and thought, wow, that's really interesting. Damn. It's also something apparently kind of ill-defined. People seem to have different ideas of what is data-oriented design and what is data-oriented orientation. I don't know, lots of names. But here's my definition for this talk at least. Know your data. Design around your data first, and only second consider objects or logical wholes. And as everything in programming, you should take this in moderation. It's probably sometimes a good idea to design around objects first and data second, but I'm not going to take it in moderation. So let's look at how data works in ECMAScript. Of course, data in ECMAScript is just the values and the heap data for that. There's prototypal inheritance in ECMAScript. There's no multiple inheritance, but the inheritance chain can change during runtime in actually two different ways. Your object can change its prototype at will, but also somebody can go change the prototypes that you are inheriting at any time. So your virtual methods can become some other methods randomly, or you can get more virtual methods suddenly. Interestingly enough, the prototype does not actually define your internal methods. The object type defines your internal methods, and internal methods are things like how do you react when you are assigned into, or what do you return when somebody reads from you. All right, so as said, an array is an object. An array buffer is an object, but it's not an array. It's completely different. Functions are objects. Everything is basically an object if it's not the primitive stuff. Array behaves like an object in every way except that it's get and set methods. So what happens when somebody assigns to you, what happens when somebody reads from you, are defined differently. And actually, now that I think about it, it's only the set method which is defined differently. Also, the spec helpfully says that whoever uses this abstract operation is an array. I don't want to be comparing function pointers to see if an object is an array. Anyway, function is exactly equal to an object. Its methods internal methods are all the same, but it has one or two extra methods, the call and construct methods. So if you look at this and you come from an object-oriented viewpoint, you're going to say, well, obviously, objects define the kind of base class, and they have virtual methods. Array inherits that object, so it overrides some of them. Function inherits object as well, and then it just adds one more or two more virtual methods, the call and construct methods. And this seems like a reasonable thing. Let's not do that. Let's instead think about how arrays are actually used. And we'll think about that first, then decide how to actually build this logical whole. So, example usage of an array in ECMAScript. They have a special property called length. It returns kind of, this is not quite true, but this is close enough. It returns the current highest index plus 1 of all index properties in the object. And if you assign an index, then the length may change. And if you assign an index that is higher than the current length, then you will create holes. So if the length grows by more than 1. If you assign length, it either drops items or creates holes if the length grows, or just might not do anything if you assign the same value. And how you normally use arrays is that you push, pop, and unshift items into the array or out of it. So those always keep the array kind of nicely compact. Always changes index by at most one. You can also sometimes create arrays with some static value, in which case it has a bunch of holes in it at that static length. And then you assign at those indexes. Sometimes you might assign length to, for instance, empty out an array. The push, pop, unshift, shift functions, those come from the prototypal inheritance. It's uncommon to put non-indexed properties into an array or to change the prototype. If you change the prototype, you're going to lose push, pop, shift, unshift, unless that prototype that you changed to also implements those. But then, like, what are you doing? Yeah, let's not look at that yet. So, and then non-indexed properties, that means properties but like foo or bar or so on and so forth. What's our time? Okay. Why would you assign those to an array? So do we actually even need the object-like properties of an array? Common usage of objects, by the way, is to assign non-indexed properties. So foo, bar, so on and so forth. It's quite rare that you would assign 0, 1, 2 to these indexes into an object. Because if you're assigning to those, like, why are you using an object? Why aren't you using an array? The spec defines a special case that the index properties of objects are listed first when you ask for the keys of an object. But that's the only special case. So do we actually need the object to kind of prepare for these index properties specially? Or could they just be normal objects, and then when you ask for keys, we'll sort them for you first? So the array and object implementation in our engine is that, no, we do not need object-like properties for arrays normally. So we don't track non-index properties in an array. We actually don't track prototypes at all either. And we don't need index properties in objects. So we don't track kind of elements of an object. We don't track these indexes in an object. Objects track the prototype and their normal prototypes, properties, be they indexed or non-indexed. Foo, bar, 0, 1, they're all tracked the same way. Arrays track elements, so those are 0, 1, 2, 3, 4 index properties, and then they have an option to an object. And this is basically an option non-zero 32-bit integer. So it's an optional index into the heap vector of objects. By default, an array is then only a collection of index properties. Its length is calculated. The prototype is inferred to be the array prototype, because why would you be changing it? It's always going to be the same. If you change the prototype of an object of an array, or you assign foo or bar into your array, then we create the backing object and we make this option sum. And that object can then do tracking of those things. We don't care. Like, it's gonna be slower, but why are you doing that? Don't do stupid things. As a result, our array is currently only 16 bytes in size. It might grow to 24. And then the number of items, or actually the capacity of the array. Okay, so where are these saved properties? You would normally think you would put stuff into a vector on the heap with a vector of values, and you would maybe inline some properties, but we have a heap vector or multiple heap vectors of arrays of values. So our heap contains vectors that prepare to have arrays of values of some defined size. So the array and object, when they point to their elements or properties, they actually have they know which value, which vector of this kind are they pointing to, and then which index in there are they pointing to, and how many items in that array do they use. And property descriptors, let's just skip that. Rarely used, so we'll skip those. All right, so what is the point here? Well, it's an entity component system. Kind of, in a way, the point is to save memory, but the point is not to save memory. The point is to save cache. So all our heap allocations, whenever you allocate on the heap, it's going to be in linear memory with data of the same type created at basically the same time. Mapping through an array is just accessing values in linear memory. And this is nothing new. Every engine does this because, of course, you're going to do your array as a vector. But now, in our engine, if your array contains data of the same type, that data is also probably going to be right next to each other because it's most commonly created at the same time. Like, let's say you map over an array and for each item you create an object. Those are going to be created right next to each other because they're created at the same time. And now GC marking the heap, normally, or always, it's just the act of iterating through all allocated objects on the heap and following their outward pointers to whatever they depend on. Now this is just traversing linear memory. We go through the vector of all objects, and for each object we check its prototype. We make sure that we know that we should look at that later. We check its properties, and we make sure to know that we should check those later. And we go through all the objects that we have marked so far, queue up these indexes for future work, and then we repeat if we still have more work to do. We put the output indexes into queues and so on. The GC sweep just becomes a retain mut on the heap vectors. So any data that was unmarked, we drop with the retain mut, and those that we retain, we make sure to shift any heap internal indexes down by the amount of data that has kind of shifted from underneath them. So after a GC, our heap vectors are always packed with live data. GC also, let's actually kind of skip these. We also get some nice benefits to how we get new space from this, but that's yeah. So at the end of the day, our engine then has it's an entity component system where our entities are the values, the components are the heap data that we keep in the vectors, and then the systems that we have are mostly our GC, but also, of course, the user code that we run on it. But they can do whatever. But yeah, we get a nice entity component system. So this is what my friend was telling me this summer or last summer. Entity component systems. He was really, really happy with those, and I was like, yeah, that sounds interesting. Let's do that for a JavaScript heap. So okay, what is Nova going to be tomorrow? So we're still very, very rough. It only runs a few trivial ECMAScript programs. Still can't call functions, for instance, which is somewhat important. But there's a lot of grunt work left to do for implementing more spec abstract operations. The VM implementation and the bytecode is just barely started, which is why we can only run some trivial programs. I have implemented the GC algorithm, but it's quite rough still. Although it's parallel, it's because it parallelizes like ridiculously easily. the heap needs to be made concurrent marking proof. I really want to mark in concurrent time, but this will be really hard. Having just a single mutator thread makes this more possible. I would like there to be, I'm not sure if there are, but I want to kind of find a Rust abstraction that gives me a way to turn my heap into a read-only copy of, or clonable structure, not structure, but kind of something that I can give to everyone. Like you can read from the heap, you can read from the heap, you can read from the heap, and then one object that is only allowed to, or that is allowed to read and write to the heap. So this is kind of like multi MPSC, but reverse. Yeah, the sweep is already stop the world, or is, yeah, it's always gonna be stop the world, and it's embarrassingly parallel. But I also want to make the heap concurrent marking mostly lock-free. So that means I will need to do some RCU, read copy update stuff, like if a heap vector needs to be reallocated, I need to actually keep the old allocation, copy it into a new larger allocation, change the pointer, change the length, and now I can keep going. And I need to keep the old vector memory alive until GC has finished. Then I know I can drop it. Also, I want to do feature flags, a lot of feature flags, so every feature flag possible. The 8-bit indexes, that would be lovely as a feature flag. Automatically frozen prototypes, feature flag, yes. ECMAScript optional features, feature flag. Safe JavaScript variants. And eventually I kind of want to be the most interesting ECMAScript engine on the Rust block. I think it already is, but I mean, it's early days, very little code, very little things to show. And the only competition, I believe, is the BOA engine, which is not very interesting. They use the GC crate. Using crates, so old-fashioned. Also, it might be nice to consider being fast, And I want to do it together with you. So it's mostly just me right now. There are some other people, but they are sometimes active, sometimes not. So grab the GitHub link, take a look at my horrible code, some others as well, and come write a JavaScript engine with us. Yeah, that's my presentation.
All right, thanks everyone. Sorry for running a little bit over the official schedule. That's all my bad because I didn't give very clear instructions to the speakers on how long the presentation should be. It felt to me that the 4 hours that we had was going to be good enough for 4 speakers, but again, we made the same mistake as we made it like 2 times past, that there probably wasn't too much or enough time, let's say, to just discuss randomly with each other. But for that, we are planning to continue somewhere from here. I don't know where. I personally need to figure out some practical stuff, like the pizza problem is still not solved, in the sense that the brown boxes need to be gotten somewhere, and I still don't quite know where. So we'll figure that out. But after that, I'll also be heading off somewhere else to continue the discussions. Other than that, we can hang out here until 9 o'clock sharp, or I think ideally we'd be out of here at 9 o'clock. So with that, thank you everyone for today, and until next time.